Hi, this is Mark. In this video, I'm going to talk about a prediction for, or a new method to predict the heat flux of a material. This is based on my graduate research. We developed a bridge or geothermal bridge de-icing system using a concrete slab of 8-inch thickness. We used a water tank that circulated fluid or heated fluid to the underside of the slab using PEX pipe that was looped in gyrations on the underside of the slab, embedded or encapsulated with geofoam for insulation. And then we measured the temperature inside the slab using thermocouples that we exported the data to an Excel spreadsheet. Now, the idea of this formula, or the first to start, you have to understand the main concept is that when you have a closed or environmental system, and we're heating a bridge slab in a freezer box, the minimum temperature we called as the ambient, or A. Now the maximum temperature is the input or inlet temperature going towards the water that enters the base of the slab on the inlet side is the maximum. And then the difference between these measurements we call the heating load. But before I begin with that, this is y-axis will be temperature, time will be x-axis. And so you start assuming that everything reaches equilibrium at the ambient temperature below freezing, the slab will be that'll be the initial condition. Then when you heat it, it's going to increase and then converge to a limit, which let's call the temperature T at position J, depth K, right here. So we measure the thermocouple at different positions, geometric positions, as well as the vertical position we call K. And we measure the temperature at a depth of 0, which is the surface, -2, -4, -6 inches, which is 6 inches below the surface, and different positions. Now, notice that the temperature is a proportion of the total heating load. This is I. Heating load is going to be I minus A. So the difference between inlet and the ambient, the heating load, the temperature at steady state represents a proportion of it. Therefore, we can predict the temperature at any position as follows. We start with the ambient right here. Because we're increasing, we're going to add a proportion we call P at JK of the heating load. So that's the prediction for the temperature. Now, when you're measuring heat flux, what you do is if you're heating or inputting heat into a slab of 8-inch thickness, what's going to happen is you have to find the temperature gradient between two positions. So we'll call this temperature 1, temperature 2 at the base, and the distance between it we're going to call change in Z. Now, another property of the material is called thermal conductivity. K is how conductive the material is. If it's more conductive, the heat flux is going to be higher. Likewise, the temperature gradient, or the difference between the lower and the higher temperature, represents the potential for heat flow. Like, for instance, you're heating coffee or you're cooling coffee. Coffee is initially hot, it's cooling towards the ambient temperature. And because the difference is large, you're going to have more heat transfer, and thus the heat flux will be higher. Basically, heat flux represents, as a quantity, it represents the amount of thermal energy flowing through the system. So we call it F for heat flux, and it's equal to negative K times delta T over delta Z. That's a temperature gradient, or negative K times T1 minus T2 over delta Z. And basically, the reason you use negative is the direction of flow. It's from hot to cold. And when you take the difference between the minimum and the maximum right here, it's also a negative. And so it cancels out and you're left with a positive heat flux. This is the actual measurement. If we get the temperature values using thermocouples, we can get the heat flux given the fact that we know the thermal conductivity, which we use a sensor, or we use some equipment to measure the thermal conductivity at many different points, and we average it, and we got a K value the thermal conductivity we found was equal to 2.2 watts per meter squared Kelvin. Now, using the original prediction, the formula to find temperature, we can now rearrange this formula to make a prediction, F prediction. We're going to set this equal to negative K. In closing brackets, we're going to have T1, which is just equal to A plus P1 times I minus A, minus, because we're taking the difference, A plus P2 I minus A, all in closing brackets. And notice that this, using distribution property, gets transferred over, but the ambient, we know A minus A is 0, so those cancel, and we're left with negative K times, using algebra, we have P1 times I minus A minus P2 times I minus A, so it's P1 minus P2 times I minus A. Oh yeah, I forgot, all divided by delta Z. Okay, so therefore now we can rearrange this as negative K delta P over delta Z times I minus A. Now we're going to define this quantity right here from here to here. We're going to define this as tau. It's a new variable. We're going to is equal to negative K times delta P over delta Z. What this represents is the potential for transmission of thermal energy into the concrete or the material. The higher the conductivity, the higher the potential, the higher the proportion gradient, the higher it's related to the temperature gradient, the more there's going to be more potential to transfer the energy from the base to the surface, and thus the heat flux is going to increase. And this represents the slope of the system. Because when we rearrange it, when we rearrange the formula, you get F prediction is now going to be tau times I minus A. And notice in algebra, when you write y equals mx plus b, linear equation, our m is equal to tau, our x is equal to I minus A. Dependent variable. Now we have a linear equation with this y-intercept of 0. And tau, of course, is the potential to transmit heat, and a heating load represents the amount of input, how much thermal energy we're inputting into the system. So as you increase that, of course, you're going to increase the heat flux. So what's interesting about this when I was doing research is when we took multiple tests, so this is number of tests, we can call n, and the proportion we found that the proportion average was about 0.092. This is 0.092. And the standard deviation phi was equal to 0.003. Very, very small. And what we found is the data points were very, very close to the average. Because the standard deviation was so small, we've assumed or stated that the proportion is relatively constant. And that's true per plane. So if you take a concrete slab and you cut it into slices, the proportion at here or the proportion at here or here, and this is the base and this is the surface, is relatively constant. Therefore, delta P over delta Z is approximately a constant. Okay, so that implies that the slope, tau, is approximately a constant, and that gives us a good prediction for heat flux. Now, I'm going to go over an example. This is going to be the conditions of we took about 13 tests in the freezer box. So for this case, the ambient was, if I remember, it's negative 3.5. It has to be degrees Celsius for this case. The inlet was equal to, I think, let's see, it was it was 34.1. degrees Celsius. The T1, the surface temperature, was approximately negative 0.06, and the base, or at a depth of 6 inches below the slab, was equal to 3.72 degrees Celsius. Another property we found was a change in proportion per unit depth was approximately 0.68 for 39 ranges. And then the thermal conductivity, of course, we measured is 2.2 watts per meter squared. So starting with the heat flux, we're going to start with F. Oops. Okay. F is going to be equal to negative K delta T over delta Z, or negative K T1 minus T2 all over delta Z. And delta Z is 6 inch difference. So we know, oops, we gotta get this closer. Delta Z was equal to 6 inches, or 0.1514 meters, because this has to be in meters. 1D heat flux. And okay, so in this case, we have, so this equals to negative 2.2 watts per meters squared Kelvin. I believe that's should be Kelvin or so forth, times, okay, so when you take Kelvin, it doesn't matter if you use degrees, in this case degrees Celsius or Kelvin. They actually, Kelvin is basically degrees Celsius plus some value, 192 I believe, or I forget the actual value, but when you take the difference, that cancels out, so it stays the same. So it doesn't matter if you use degrees Celsius in this case. This one is going to be negative 0.06 minus 3.72 all over 0.1514. Okay. And what we get is 54.92 watts per, in this case, the K's cancel. Let's see. I think this is meters Kelvin, watts per meters Kelvin, and this is going to be watts per meters squared. That's the actual that's the actual formula. So thermal conductivity should be in meters, watts per meters Kelvin. If I look, so now with this formula, it's about 55 watts per meter squared. That's the measurement of thermal conductivity. Now the prediction. So we're going to get here, and we just calculate negative K times delta P over delta Z times heating load. Okay, so in this case, we have negative 2.2. Delta P over is 0.68 times, go back to the formula, go back to the conditions, 34.1 minus, okay, so we have 34, oops, so we have 34.1 minus negative 3.5. And that's it. And then when you calculate this, you get approximately 56 watts per meter squared. Right here, the proportion is constant. The proportion, so we know change in P over delta Z is equal to 1 over meter. That's the value, and this meters times meters gives you the meter squared. The K cancels out with the degrees, so you're left with this unit. Now, the difference, now we know this, so if we look at the prediction minus the actual value, So we take 56 minus 55.9, or 54.92. Yeah, 54. And we get a value of 1.08 watts per meter squared, which is very, very small. And the reason for that, when we did our tests, we look at the equation. So right here we have a heating load as the x variable. This is a heat flux prediction, or heat flux. And we get a line, it's linear, and with the slope equal to tau over 1. If you increase the heating load by 1, that means that flux increases by slope, or the slope of tau. And what we found is the values, actual values, were pretty close to the line, and the R squared value was 0.957, which is very close to 1. 1 means that your value, all the points are on the line. If R squared is 0, approaching 0, that means it's no relationship. It's scattered. There's no correlation at all. This is a positive correlation, but it's a very strong one. And that's kind of exemplified right here. And the interesting thing about this is we know, like, if you take the material, the proportion is a function of the conductivity, the heat diffusivity, all the properties of material. If you can relay this and get the proportion and figure out that for the material, or if you can figure out the delta P over delta Z per material, you find it's a function of some values, then, and you know the thermal conductivity, then you can get a reasonable prediction using this formula, because these variables are relatively constant. Now, the last formula I'm going to mention is, this was interesting because when we were doing bridge de-icing, imagine you have a bridge. This is the surface, a bird's eye view. Here is the outlet end. So if you imagine we have pipes at the underside of the slab. This is the inlet end, this is the outlet end. Of course, the temperature, the inlet is going to be greater than the outlet. This is the max. This is the minimum. Obviously, well, the minimum should be at the perimeter over here. So if we take this section right here, if we were to create global de-icing, meaning instead of local, global means we de-ice the whole slab, we want to focus on the thermal minimum. That was the idea. But I thought we considered in our research, what if we can get the slab temperature reasonably above freezing? So let's create a design temperature. We call it T design equals to TJK, our temperature, because obviously this is assuming we haven't measured it yet, because we know the proportion. We know the average proportion. This is we don't even need to measure the temperature. We want to target a temperature, so we're targeting it, and we're going to equate it to A plus delta T design. So suppose we want to design, our T design is 34 degrees Fahrenheit. Reasonably, it's above freezing, and it gives us some room for error. And of course, if we want to de-ice the whole slab or supply enough energy, we want to make it above 32. And then our delta, or ambient, let's say our ambient is going to be 25. Therefore, our delta T design in this case would be 34 minus 25 is 9 degrees Celsius, Fahrenheit. So using this original equation, we can write TJK equals A plus delta T design, which equals to A plus PJK times I minus A. Using this formula now, we can cancel out the A, and we're left with delta T design equals to PJK times I minus A. Dividing both sides by P, we have delta T design divided by PJK equals inlet minus ambient. And then we add A to both sides with delta T design over P plus A equals our inlet temperature, which is what we want to find the water temperature we need to supply to get the temperature of the slab to 34. So now let's, using our average proportion, we're going to assume now for simplicity it's 0.1. Okay, so using our design parameters, we're going to write our I equals to 9 divided by 0.1 plus 25, because that's our A, ambient, or 90 plus 25 gives us a temperature of 115 degrees. That's our water temperature we need to get the temperature of the slab average to 34. And this is following the equation. TJK is equal to 25A, that's A, plus the proportion, times the I, which is 115 minus 25, which is 25 plus 0.1 times 90. 25 plus 9 gives us 34. And that is the average, using the average proportion. So if we were to assume average, so if we make this uniform, the pipes, geometrically symmetric, assuming we take the midpoint of the slab, we can assume the P average is about the midpoint, right? And that means this side of the slab towards the inlet end is going to be greater than 34. This side is going to be assumed to be less than 34. Therefore, we know that the right side probabilistically is going to de-ice. We know, though, as you approach this boundary right here, the probability decreases. But because we added the design to 34, it's a higher probability in the beginning. But logically, it would make more sense. What if we could take this is the outlet, this is the inlet. We take this section and we find a proportion minimum. So redesigning this, we could say the I maximum is equal to delta T design over P minimum plus A. And using this formula, what we find is if we set the X variable to or P proportion, we write the formula, so T design over P equals I minus A. This is our inlet temperature. And what we find is as P approaches 0, I approaches infinity, and as P approaches 1, let's say this is a 1, I approaches 34. I minus A approaches 34. Or this would be I. I approaches 34, which is the actual temperature that we're trying to design it to. And the reason that works is like we had a temperature design of 9 divided by 1 plus 25 gives us what? 9 plus 25, 34. But if we take 0, proportion is 0, it's undefined. This is undefined. It's not defined. It's infinity. So that just shows the efficiency of this system decreases rapidly as you get below 0.1 for the proportion. You want to ideally add thermal materials, the conductive materials, maybe add it to the concrete like graphene to increase K. You want to go up. If K goes up, implies that the proportion's likely going to go up and so forth. And you want the proportion to approach 1 because we know that 0 is less than P is less than 1. It's between 0 and 1. But we want the P to approach 1 for maximum efficiency and minimum heat loss. But anyways, yeah, this is the equations that we use to develop a model for predicting the amount of heat or thermal energy we need for de-icing, bridge de-icing. But anyways, I'll stop here. I hope you enjoyed, and I will see you next time.